over some of the things in chapter 26. And hold on, gotta get my book. And it deals with the electric field. So the big idea to start off with is the general formula for the electric field is E equals F over Q. It is a ratio of the force on a charge divided by the amount of the charge. So that is the general formula for something. So we'll make that in pink. At any rate, these are specifics in terms of figuring out the electric field strength at distances from different geometric shapes of charges. So there's a couple which I think are important and a couple not that important. And this is a really important one. It's the electric field strength at a distance from a point charge. So that's KQ over R squared. That's actually your formula. It is not on your formula sheet, but it is important to know. How do you get it? How do you derive that? Well, if you look at Coulomb's law, which is formula 1 E1 on your formula sheet, which is basically K, Q1 times Q2 over the distance squared between them, and that's an electric force between two charges. So to define the electric field, you'd put that in the numerator of this equation and divide it by Q. Well, one of the Q's cancels out. Specifically, the Q that is the source charge, meaning that at a distance from where you are measuring, is the one that does not cancel out. So the big idea here is the source charge multiplied by a constant divided by the distance squared gives you an electric field strength. This is similar to the Earth's gravitational field strength, which decreases via an inverse square as well. Now, on your formula sheet, you see a lot of these things, 1 over 4 pi epsilon sub 0. That epsilon sub 0 is vacuum permittivity. Vacuum permittivity is a constant, which is 8.85 times 10 to the negative 12th. And oftentimes it's multiplied by 4 pi. That's similar to the mu sub 0 or vacuum permeability that we've talked about with magnetism. So why would you use this instead of this k, which is simply 9 times 10 to the positive ninth? Here, I wouldn't. I would go ahead and use this. In reality, though, this epsilon sub 0 helps with some fundamental understandings, which we'll even see later in this chapter. So the AP doesn't give you two different versions of the formula. I like to use this one, just like I like to use K, Q1, Q2 over distance squared for Coulomb's law. At any rate, so from a point charge, we have an inverse squared relationship. And it's important to remember that the electric field is a vector quantity, points away from positive charges, points to negative charges. Also, if you have multiple point sources, you would need to figure out the vector sum of an electric field at any one point caused by all of them. Now, if you can find the net force at any one point using Coulomb's law, the easy way to get the electric field at that point is simply to divide that electric force by the charge at that location. However, again, an electric field, divided by the source charge, and that could be a little bit more difficult. At any rate, electric field strength, an electric field at a point in space does not need to have a charge at that point in space. In other words, similar to gravity, if you have a mass, it creates a gravitational field, whether or not there's other masses around. If you have two masses and they each create a gravitational field, they interact and cause a force between them. Similarly here, two forces through Coulomb's law, or two charges through Coulomb's law, cause an electric force between them. But each individual charge causes an electric field. You don't need two electric charges to cause an electric field, as noted in this formula. Okay, so that's an important one. Notice if I skip over here, it's the same formula for a charged sphere. So the reason that that's important is if we have a sphere with a significant radius, inside that sphere, the electric field is going to be 0 at all times, as long as the charges are distributed electrostatically so that they're not moving at that point. So the reason for that is if you think of either a solid or a hollow sphere, all the charges would tend to go to the outside. Therefore, vectorially inside the sphere, the electric field is zero. And in fact, that's true inside any conductor. Now, in a non-conducting sphere, that can be different because the charges wouldn't all exist on the outside. So outside of the radius of the sphere, when lowercase r is greater than the radius of the sphere, this looks exactly the same as what we had over here. Inside the conducting surface, it would not. And again, we can talk about that as time goes on. Yeah, I can do that at some point. Because if you have a non-conducting sphere with charge spread uniform throughout, it's a little different than that. Basically, the electric field strength goes up linearly as you go away from the surface, which is also true gravitationally, by the way. But then it decreases via the inverse squared once you get out from the surface. But for conductors, zero inside and this outside. Okay, for what about long wires and infinitely charged planes? Well, those are a little bit different. You might imagine that because a wire is going throughout a line through space, that the electric field changes differently than from a point source. And that's true. For an infinitely long wire, it decreases inversely as you get further from the wire, not inverse squared. So if you could picture like a pole, like a fireman's pole going from floor to ceiling, and you can think of the electric field pointing radially out, assuming that the wire would have positive charges, or pointing inward if the wire has negative charges, it makes sense that that would decrease as you get further away from the pole. At the end of the chapter, or at the end of these notes, I'm going to show a couple diagrams related to that. So this lambda stands for linear charge density. It's coulombs per meter. So hopefully it makes sense. You have a stronger electric field if you have more excess charges per meter, and you have less electric field strength as you get further from the wire. For an infinitely charged plane, we have something like this. Now, notice this is kind of interesting because it's equal to this weird N shape, not on your formula sheet again. Stands for charge per unit area, so that's charge density in terms of area. And you've got that as a constant and divided by twice times this vacuum permittivity. What that says is if you get further away from an infinitely charged plane, the field does not get weaker. Now that might seem weird, but in practice, something that's infinity has charges going on forever. In real practice, what this means is in a capacitor, if you're toward the center and not on the fringes of a capacitor, the electric field strength in the capacitor is constant everywhere. And its formula looks a little different than this. So we'll see that a little bit later. But if it's an infinite plane, essentially that means your distance to the edge would be much, much greater than your distance, say, between the plates or things like that. Section 27.2 is a field model of multiple charges, including dipoles. Your author for this textbook really likes dipoles, and he talks about it again, I think, toward the end in section 26.6, 26.7, somewhere like that, and I'll look up at that in just a minute here. But the main thing you need to know is a dipole is a molecule that's got a partial positive and a partial negative on it. And so it actually can create something called a dipole moment. I don't think that's important. I think you could predict the electric field in between a dipole if you know the amount of charge and how far apart they are. So field lines, again, pointing from positive to negative. I'm not going to worry too much about dipoles. For 26.5, now notice I've skipped 26.3 and 26.4. I guess I should tell you about that. So 26.3 and 26.4 deal with quite particular ideas of like how you solve for certain distributions of charge. So things like a line of charge that's not infinite in length, or a ring of charges, or a disk of charges, or things like that. I think they're useful to look at the pictures to think about them and try to interpret them that way. I don't think mathematically you want to look at that in terms of, say, your formulas in the textbook and so forth. And the reason for that is, again, they're very complicated. They can get complicated, and they depend a lot on specific distances. Big idea is if you have got a disk of charge, if you're pretty close to the disk, it acts like essentially a sheet, like what we had up here. If it's a large disk and you're pretty close. If you're far away from it, things tend to act like a point source. You have a lot of charges on that disk, but if the disk is fairly small compared to how far away you are from it, it's going to act like a point source. So that's kind of the big idea. Figure 26.15 on page 761 shows like a ring and how there's a certain distance where the electric field becomes maximum. So if you're at the center of the ring of charge, you've got zero electric field. And then if you get very, very far away, you have zero electric field. And then there's a distance in between where it's not. At any rate, like I said, I think those complex shapes are a little bit things we don't need to focus on right now. 26.5 deals with a parallel plate capacitor, and that is actually an important application. We've talked about capacitors before. We've used them in lab, so we're not that far behind with this. The idea here is the electric field in between the plates of a capacitor doesn't depend necessarily on how far away the plates are from each other, as long as the plates are large compared to like your distance from an edge. So what does it depend on? The charge density. So that's Q over A, that's that weird N symbol. So that's N over E sub 0 or vacuum permittivity. Now if you look, you're like, well, that looks awfully familiar to what we saw earlier on the previous page. Notice there's a 2 in here. And it is similar, but Q is the charge on each plate. So if you think about an electric field in between two plates with charges on each one, that's why in this case that you would get rid of the 2. At least that's my understanding of it. So charge density divided by vacuum permittivity. Pretty easy to understand that. And that's inside the plates of a capacitor. Outside the capacitor, except for the fringes, the electric field would be 0 because, again, the net charge is 0. And we normally assume that the plates are very close together compared to your distance from outside. So here, if we normally have a uniform field in a capacitor, we'd say go back to the general formula for capacitance, or for electric field, force on a charge between the capacitors divided by the charge placed between the plates. So this gets you the net force on something. This is actually kind of important. And by the way, this formula, which looks a little different than Gauss's law, but is really similar to formula E3 in your formula sheet. And so what it does is this does relate back to Gauss's law. And if you forget this, it's formula E3. At any rate, so let's say you have something where you're trying to figure out how much a charge is going to be accelerated in either between a capacitor and an electric field. Well, we go back to Newton's second law, law of acceleration, always comes back to this. And if the electric field is force over charge, then we basically get m times a would be the force over q. So if we want to find the acceleration, we rearrange that. The force is equal to E times Q, rearranging this formula, divided by mass. Here's why that's important. I'll give an example of it. If you have a proton and an electron, and they're both put in the same electric field, first of all, they're going to accelerate in opposite directions because electron has a negative charge, proton has a positive charge. You might think they would accelerate at the same rate, but they don't, because although they have the same net charge on them, 1.6 times 10 to the negative 19th coulombs, they actually have a very different mass from each other. So a proton has about 2,000 times the amount of mass of an electron, and therefore a proton's going to have much less acceleration than an electron if they're both in the same electric field. Examples of this? Well, back in old style TVs, the cathode ray type, which are the fat TVs that you might still see occasionally from place to place, or at our school, we've got those. Those are basically cathode ray tubes. There's other things that are used for cathode ray tubes. Certain medical equipment like EKGs, I think, are projected on it still. I've got an oscilloscope and so forth, and essentially those get shot by being projected through capacitors. And so those electrons end up being deflected as the electric field changes, and that created the picture in the screen, depending on where they ended up. So example 26.9 on page 769 is actually a really good question related to how the AP might ask you questions about things. It deals with acceleration and deflection in a capacitor. 26.7, and you might say again, what about 26.6? Well, okay, that's kind of what I just talked about with forces on charges in electric fields. And 6.7 deals with motion of a dipole in an electric field. Again, not a big deal. You should recognize if you've got a molecule that's got a partial positive and a partial negative, if there's no net charge on it, there'd be no net force. But there can be a net torque, which is interesting, and that's shown in figure 26.29 on page 770. An idea of how you would figure that out. So the idea is, if you have something like this, it's going to align itself up. The dipole will align itself up with the negative end pointing toward the electric field source and the positive end pointing away. Because we, by convention, think of the electric field source as being toward a positive area. And there's another good picture showing what would happen if you had, in figures 26.31 on page 771, if you had a non-uniform electric field, how would the dipole align with respect to that? So, cool fact, in microwave ovens, the electric field switches many, many times per second. I'm trying to think about how many megahertz they are, but there's a lot. And essentially that causes polar molecules like water to rotate back and forth very quickly, which basically means that the water molecules rub against other molecules and they heat it up. So it's really molecular friction, which is kind of how a microwave works. So here's some sample diagrams. If you had a single positive charge, you'd show the electric field lines pointing away from it. And so how close these lines are to each other is a relative way of talking about electric field strength. So here, very close to this positive charge, the lines are close together. We have a strong electric field. Here, further away, the lines are further apart, and we have a weaker electric field. Over here, we've got two positive charges. The electric field lines would basically do something like this. You can see that they push against each other. Exactly in between, the electric field would be 0. And if it was a little bit closer to this one, the electric field would point up. Here, the electric field would point down. Here, the electric field would point only to the right as the vertical parts cancel out. And here it would point to the left as the vertical parts cancel out. If we have something with a positive and negative, we have a strongest electric field in between them, and we have a weaker electric field around here like this. If we want to think about uniform electric fields, if we have a bunch of negative charges down here, we would show a strong electric field with the field lines being close together, not many negatives, or a low charge density would show the electric field being weaker with the lines further apart. So hopefully that helps your understanding. I'm going to upload a couple other resources as well.